Okay, so today's talk is an introduction to analog IC design. And this is an introductory course. This is not meant for analog designers or analog layout designers. You guys already know all this stuff. This is meant for the people that don't do analog design and layout every day. And I'm trying to give you an education on what the design community does. Okay, the talk is divided into two sections today. I'm going to be spending the first half of the talk on matching. Why do we like matching? Why is it needed for analog circuits? And then going through a bit about how we create match devices. Second part of the talk is going to be current mirrors. Everything you'd ever wanted to know, or maybe you never wanted to know about current mirrors. Current mirrors are very, very important in analog design. So that's why I'm going to spend a lot of time on those. There'll be a quiz at the end. Okay, so at first glance, analog IC schematics and layouts, they can look really complicated and confusing. However, most analog circuits are designed using a common set of practices. And once you start to recognize these practices and techniques, things get a lot easier to follow. My main goal today is to introduce you to some of the more common concepts used in both analog design and analog layout. However, my ulterior motive is to familiarize you with as many of the commonly used terms in the IC industry as possible. So if you're designing a circuit for, say, a printed circuit board, you can often specify the exact components you need. For example, if your circuit requires a very precise resistor, you can specify a 1% resistor, even maybe a 0.5% resistor. On an IC, you also get to pick your component values, but you don't get to pick your tolerance. You get whatever the fab gives you. And that's often plus or minus 20%. It could even be plus or minus 30%, especially if Jim is involved here.
40%.
40%, all right. Okay, so let's say you want to design a circuit that requires a 2K resistor. However, what you're going to get is maybe 2K plus or minus 20%. So that means that resistor might be as low as 1.6K and as high as 2.4. So if the output of your circuit relies on the absolute value of this resistor, you're going to see a lot of variation. And that's typically not what you want. It's typically undesirable. Now, of course, you can always trim it using fuses, EEPROMs, thin film resistors. All that stuff is expensive, time-consuming. We'd like to avoid that if possible, or at least minimize trim. So even though IC fabrication processes have some difficulties hitting precise exact values, they make up for it in other ways. All the transistors, diodes, resistors on a particular wafer have seen the exact same set of oxidations, diffusions, implants, heat treatments, mask alignments, etc. Because component A has seen the exact same process steps as component B, they'll track each other very well. And for example, let's consider that 2K resistor we talked about earlier. What would you expect to see if we put two of these resistors, A and B, on the same wafer? Since each resistor has been exposed to the exact same fab process steps, you would expect them to be nearly identical in value. Resistor A, if it was 1.6K, you'd assume resistor B is also going to be 1.6K. Similarly, if resistor A is all the way up to 2.4K, resistor B should be at 2.4K also. Analog IC designers take advantage of this property by building circuits that depend on the match of components, not the absolute value of components. This is a key principle in analog IC design. Typically, components will match within 1% or less. This gives the analog IC designers a tool for making very precision circuits. Now, we've all heard the joke about real estate. You know, the three most important things in real estate are location, location, location. In analog design, it's matching, matching, and matching. So keep that in mind. Bill's giving me the stink eye. Okay, so this matching concept applies to all types of IC components, transistors, diodes, resistors, etc. However, for me, it's easiest to demonstrate using polysilicon resistors just because of their simple structure. And I'm going to review the structure for a polysilicon resistor, and then we'll talk about matching. So here's a top view and a cross-sectional view of a typical polysilicon resistor. The resistor heads, right here and right here, are designed to make good resistive ohmic contact with the metal and with the body of the resistor. The body of the resistor is designed to create a known, well-controlled sheet resistance. So you may recall that sheet resistance has units of ohms per square. So let's assume the high sheet row poly layer has a nominal resistance of 1 kilo ohm per square. We don't count the resistor heads when we're figuring out the number of squares. So this particular resistor has 5 squares. 1, 2, 3, 4, 5. So the nominal value of this resistor would be 5 squares times 1 kilo ohm per square. That gives you 5 kilo ohms. So the combined resistance of the two heads is way, way, way lower than 5 kilo ohms. So note how the resistor contacts are drawn here. So instead of one big contact, the fab uses a bunch of smaller contacts, and they're all the same size. That's done so that it's easier for the fab. They only have to clear one size contact. You clear that one size contact, and all the contacts on the whole wafer are open. Back in the old days, we had contacts, they were all different sizes and made it very, very difficult on the fab. By standardizing on a single contact size, that makes it much more consistent. Now that we've reviewed how poly resistors are constructed, I want to discuss how to draw the resistors to maximize their match. IC designers and layout designers use multiple techniques to improve component matching. And I'm going to show how these techniques apply to polysilicon resistors. However, these same methods can be used for a wide variety of other components. So let's say you're designing a circuit that requires the match between two 2K resistors. What would be the best way to draw them? Let's look at this set on the left side here. You have all these resistors are 2K. And they're all 2 squares of poly, but you have 2 resistors that are drawn the same size and 2 resistors that are drawn different. I think it should be pretty much obvious if you want the resistors to match. You want to draw them exactly alike. You just not the same number of squares. You want them to be drawn exactly alike. How about over here? We have 2 resistors that are close to each other or 2 resistors that are pretty far away from each other. Again, I think it should be pretty clear. If you want matching, you want to put them close to each other. And this is because you get gradients that go across the wafer. Say the poly sheet row might at one side of the wafer be a little higher than the other side of the wafer. You get a gradient as it goes across the wafer. If you can put your match devices closer to each other, they'll both see almost the same part of that gradient. You won't see as much difference between them. How about this one? We have 2 resistors oriented in the same direction or 2 oriented in a different direction. I think, again, it should be pretty obvious. You want, if you're trying to match, you orient them the same direction. Now, this last example, let's say we have 2 resistors that are relatively fat and 2 resistors that are kind of skinny. Which of these would match better? And here you're going to get rid of the skinny resistors. The larger devices are going to tend to match better. And that's because of CD variation. These things don't always print the same every time. And a slight variation in size can affect the skinny resistors way more than that same slight variation in size of the large resistors. So generally, large components are going to match better than small components. We did talk about gradients across the wafer. There is going to be a gradient, and these larger components are going to see a little more of that gradient, but typically that's swamped out by the improvement in CD variation. Okay, so now how about this? We have 2 resistors drawn the same. The only difference is they're oriented vertically or horizontally. And in this case, it's a tie. It really doesn't matter how you orient them. Both of these are just equally as good as each other. So this is matching basics. So if you want devices to match. The basics are draw them exactly with the same dimensions and layers, both above and below, orient them in the same direction, and place them close to each other. And lastly, make the dimensions fairly large compared to the expected variation in CDs. Now I'd like to talk about a few of the techniques we use when matching is more critical, and you'll see these a lot in analog circuits. This first technique is called the common centroid configuration or arrangement. And let's say you have two resistors, resistor A and resistor B, and you want them to match very well. Well, what you can do is you can take resistor A and you chop it up into a bunch of smaller pieces. In this case, we chopped it up into two pieces. But you could have chopped it up into many more if you really wanted to match better. Same thing for resistor B. And now when we lay these things out on the IC, we arrange them symmetrically around a common center point. So resistor A is really made up of two components in series, and resistor B is really made up of two components in series. And this is done, again, to try to null out matching due to gradients. Let's say you have this gradient coming across the wafer. This could be variations in poly sheet row. You can see it might affect this resistor up here the most, and maybe this resistor down here the least, and maybe the ones in the middle, in the middle of these two. So again, this nulls out the gradients, or at least you're making an attempt to null out any gradients coming across the wafer by using this technique. And again, this is called common centroid. Okay, so moving along with other advanced matching techniques. This shows an alternate way to cancel out gradients. So I'm not exactly sure what the proper name for this structure is. However, it's generally referred to as ABBA. And I think it's pretty obvious why. So once again, this is done to try to cancel out gradients coming across the wafer. So let's say you have this gradient. Again, it could be poly sheet row, it could be critical dimensions, could be temperature. It's going to affect the closest resistor first and the furthest resistor the least, and the ones in the middle, mid-range. So again, this is a technique very commonly used for canceling out gradients across the wafer if you need very precise matching. So all the components on the wafer, they're printed photographically, and their proximity to other geometries can affect how they're printed and how they're etched. So adding dummy devices, that's these devices on the outside here, to the pattern can give you all the devices on the inside the same proximity to other geometries. So resistor A here is right next to another resistor, right next to another resistor. Resistor B is right next to your next door neighbors, look exactly the same. That's going to make all these inside resistors match better. Now, these dummy devices, they really have no electrical purpose. They're in fact, usually we tie them off to a supply somewhere like ground or VDD. They're just there for printing purposes and to make the processing work better as far as matching. So this technique is used to improve matching at the expense of adding some die area, because you're adding a bunch of devices in here that aren't really doing anything from an electrical standpoint. So dummy devices can also be used with that centroid arrangement. And here I show just a two resistor centroid with a couple of dummy devices placed around it. Sometimes they're only placed along the sides of the center devices. But if you really needed to match to some great extreme, you'd possibly put dummy devices all the way around here. That would make every device look very similar to every other device. Techniques like this are used in very critical applications like analog to digital converters. Pointing at Jonathan there. So IC designers, we're not always interested in matching two identical geometries. Sometimes we're interested in creating exact ratios between multiple geometries. And once again, I intend to demonstrate ratioing techniques using polysilicon resistors. However, these same methods can be used for a wide variety of other devices, transistors, diodes, capacitors, etc. So let's say you want an exact ratio between a 2K resistor and a 1K resistor. Well, one way to do it is shown above here. And at least the resistors are drawn the same width and they're oriented in the same direction. Yeah, it's a pretty good start. However, the contact resistance of the heads are going to present a problem. Now, we said the head resistance was very small compared to the resistance of the body. So it normally doesn't have much of an effect on the total resistance value. And that's true. However, if you're trying to get an exact 2-to-1 ratio, the head resistance is a source of error because it doesn't ratio, at least in this configuration, it doesn't ratio. A better way to draw this is shown above here. Now, in this arrangement, the 2K resistor is created by placing two 1K resistors together and then just hooking them up in series. So in this arrangement, the 1K resistors that you're adding are going to match the original 1K resistor fairly well. So it's the exact same geometry. And we'll also get a ratioing of the head resistance. So this gives us a much better way of creating our 2-to-1 ratio. This technique is known as the unit cell approach, and it's another one of the basic principles of analog IC design. And basically, if you want to achieve an exact ratio between geometries, build them out of some common cell, and then use the matching techniques we discussed earlier, like common centroid, ABBA, dummy devices, to make all those identical common cells match very well. So this unit cell concept, yeah, it's pretty straightforward. However, things can get a little bit complicated when you start trying to ratio multiple devices at the same time. And I'm not going to go into this in a whole lot of detail. However, I do want to show one specific example how this works. In a CMOS bandgap reference, we commonly ratio the emitter areas of substrate PNP transistors, these guys down here, to generate what's known as a current that's proportional to absolute temperature. By the way, that's what PTAT stands for, proportional to absolute temperature. So when you hear designers talk about PTAT, they're talking about a current or voltage that is proportional to temperature, it rises with temperature. So to make this circuit work, and I'm not going to get into this today, but next month I'll talk about this circuit, you need a ratio of these emitter areas that's greater than 1. Now, it could be 3, it could be 5, it could be whatever. For this example, I'm going to pick a ratio of 1:8. And I'm going to show you on the next slide why I've picked that ratio. So instead of drawing this as one tiny little transistor and one large transistor with 8 times the emitter area, I'm going to draw it as one small transistor and then 8 more of those small transistors all hooked together. This is the unit cell approach. You know, these will all match very well because they're all drawn exactly the same way. So that gives me my exact 1:8 ratio. Now in the layout, what we're going to do is we're going to take that one transistor and we're going to put it smack dab in the middle of the other 8. The other 8 are going to be arranged around the outside. So we're doing this in the layout to achieve the best match between this one transistor in the middle and all these other 8 that are coming around it. Once again, we're trying to maybe cancel out gradients as they're coming across the wafer here. So this just shows one example of trying to match with a ratio as opposed to just match 2 identical devices. The next topic I want to hit is isotherms. Isotherms refer to lines of constant temperature. And for most integrated circuits, it's really difficult to determine exactly where isotherm lines lie. However, for certain ICs, you can take an educated guess. And if you have an idea where the isotherm lines lie, you can use this knowledge to potentially help null out mismatches on critical devices due to temperature. Now, for many chips, like op-amps, the output devices or transistors are the main source of power dissipation. This means the die will be hottest near the output devices and cooler the further away from the output devices you move. So typically these output transistors are located along one side of the chip. And if you treat that maybe as a point heat source, you can estimate where the isotherms might be. Of course, computer modeling of heat flow and power dissipation going to be a lot more accurate than hand estimates, but sometimes you just have to use the tools that you have available. So here's an example. Say we have an op amp, and here's a very simplistic layout of this op amp. We have a couple of bond pads, we have our output transistors along one edge over here, and you can see that we're treating that as our heat source. So the die is going to be hot in this area and cooler the further away from the output transistors you get. So if you had components that you wanted to match, you typically want to put them on the same isotherm here. You wouldn't want to locate one at the cool end of the die and one at the hot end of the die. That would probably be a bad idea. As an example, if you had two resistors and you were trying to match them, it would probably be better to draw them horizontally as opposed to vertically. If you drew them vertically, one of them is always going to be a little closer to the output transistor, and that resistor is always going to be a little bit hotter. Again, you would probably draw these using those fancy layout techniques, centroid, ABBA, dummy resistors, and all those techniques are in here to null out these type of gradients. Temperature is a gradient, CDs are a gradient, poly sheet row is a gradient, and all of these fancy techniques will null out a lot of these gradients. But a lot of times you can just say, boy, I'm looking at the chip, I know where the hot spot is. I'm going to orient things to try to take advantage of that knowledge. So this is really going back in the old days. Sometimes I've even seen people try to offset resistors if they aren't right smack on the center line, where they'll try to guess exactly where the isotherm is and offset the resistors. I haven't seen this done in a long time, but it could happen. Okay, the next thing I want to talk about is external sources of mismatch. And this is mainly mechanical stress. And this is usually caused by the package. And silicon is a PCO resistive material. That means if you apply mechanical stress to a silicon crystal, the resistivity of the crystal can change. And if you had a matched pair of devices and you applied unequal stress to them, it could cause a mismatch. Mechanical stress is typically higher near the corners of the die. So one possible way to mitigate this effect is to try to locate the critically matched devices closer to the center of the die. If you have something that's very critical, the recommendation is don't put it in the corner of the die. Put it in the middle of the die. So if you had like an onboard ADC, it would go right in the middle. Band gap reference, you'd want to put that right in the middle. So anything that requires very critical matching, put it in close to the middle of the die to get the least amount of mechanical stress on that location. So plastic packages are made by injecting a mold compound around the silicon die that's been attached to a metallic lead frame, just like I show in this diagram over here. However, this structure can sometimes cause point stresses on the die. Plastic is an amorphous material, so the atoms are arranged rather randomly. So in addition, plastic is somewhat of an aggregate with silicon nodules mixed inside a polymer material. And sometimes these silicon nodules have sharp corners that come in contact with the surface of the die. And this can create point stresses on the silicon crystal. Now, if a point stress falls right on top of the component you're trying to match, it could cause a mismatch that can't be nulled out by any of these fancy layout techniques I've talked about earlier, like common centroiding or ABBA. And to illustrate this, I have a very simplistic package drawing here. This is a plastic package. We're kind of looking at it end on here. We have our leads and lead frame here. We have our die attached to a die attach paddle. The die is represented by this red box here. Most of the thickness of the die is just here for mechanical stress. The actual devices are just placed in the first couple of microns of the wafer up on top here. If you have a plastic material and it has silicon nodules all throughout this plastic material, some of them might be coming in contact with the surface of the die. And they can press right on the surface of the die, creating a point stress. And if you're trying to match the device that's right underneath that point stress, you're just out of luck. That device will not match anything else, and your carefully designed circuit that relies on super matching is just out the window now. So what can you do about this? Well, the solution is to coat the surface of the die in polyimide. That's what this green layer here is representing. And polyimide is a much softer material, and it will tend to spread out or absorb the stress from this silicate nodule. And so that relieves a lot of the stress that you get on the chip below. So the recommendation is if you need a high level of matching in a plastic package, polyimide coating is recommended. Here's a slide courtesy of Jim. Thank you very much, Jim, for sending me the slide. This shows an improvement in offset voltage of 1 op amps, and this is in an SOIC package, so a plastic package. And this was an improvement done by just adding polyimide to the die. And so this is graphs of offset voltage, and offset voltage is usually a very critical function of the input matching devices, mainly the differential pair, but also the current mirrors and current sources on the inputs. You can see by adding polyimide, we reduced the distribution from maybe 100 plus or minus 150 microvolts down to maybe plus or minus 50 microvolts. So this was a big deal as far as yield. I think the actual limit was plus or minus 75 microvolts of room. So this is just to illustrate the benefit you can get in plastic packages by adding polyimide. Okay, moving on to the second part of the talk, current mirrors. Current mirrors are a common building block in analog circuits, and the basic idea of a current mirror is to replicate a reference current in another branch of the circuit, hence the name mirror. These currents can be DC, meaning large signal, or AC, meaning small signal. And here's a very simple conceptual schematic to illustrate this point. If you have this reference current on the left side here, is forced on the left, and ideal current mirror will produce an exact copy of that current on the right here. Now, current mirrors also can sink current as well as source current, and here we just show an ideal current sinking. So in this case, our reference current is going into the current mirror, and the current mirror produces an identical sinking current. So both sinking and sourcing configurations are commonly used in integrated circuits, and you can cascade sinking and sourcing together to create multiple copies of the same current over and over again. So in addition to making identical copies of a reference current mirrors can also be designed with a scale factor. Now the scale factor must be positive. However, it can be greater than 1, less than 1, or equal to 1. Obviously, if the scale factor is greater than 1, it's sort of an amplified version of the reference current. And if it's less than 1, you're talking about maybe an attenuated version of the reference current. So let's just hit ideal current mirrors for a second. An ideal current mirror will faithfully reproduce some reference current, even if you vary VDD up and down. And this is known as power supply rejection ratio. You'd like this current mirror to work, even if VDD is moved around. In addition, you'd like the output current here to be independent of load. You'd like to be able to move this load impedance all over the place and still get the same output current. Now, this usually works over a wide range of loads, but you can kind of see once the load impedance gets too high, the voltage at this point is going to rise and the current mirror is no longer going to work anymore. But it generally works over a wide range of loads. Okay, so that's the basic theory behind current mirrors. Now I'm going to start showing you some circuitry on how we build these current mirrors. Here's an example of a basic PMOS current mirror. Transistor P1 here is hooked up in what's known as a diode connected configuration. And diode connected for MOS devices mean anytime you see the gate connected to the drain, that device is diode connected. And you can have these for PMOS devices or for NMOS devices. So anytime you hear one of these designers talk about diode connected devices, this is what they're talking about. talking about a transistor with its gate connected to its drain. Let's look at this IREF current. Since this current is going to ground, it's going to tend to pull the gates of P1 and P2 down. So as it pulls the gate down, eventually you're going to develop enough VGS on this PMOS device, P1, to turn it on. And it's going to start conducting. And eventually you're going to reach an equilibrium, and this is where this gate is pulled down just enough so that the current through P1 is equal to IREF. And there's some negative feedback involved here. If you turn on the P1 device too hard, the current from VDD is going to be larger than VREF, and it's going to pull this gate up. When you pull the gate up, it shuts the P1 device off. Now IREF can pull it back down to the right voltage so that this thing is just cracked on just enough so that it pulls the IREF current through it. It's a little hard to explain, but you can kind of see there's going to be a negative feedback in here where P1 is going to turn itself on or self-bias to just the right voltage so that you can pull the reference current through it. So this arrangement not only creates a VGS across P1, it also creates that same VGS across P2 because P1 and P2 are hooked in parallel. They have the same gate voltage and the same source voltage, so they have the same VGS. So as long as the drain to source voltage of P2 is high enough to keep it in saturation mode, P2 is going to resemble a current source. And I know that's not obvious to you right now, but I'm going to try to explain that in more detail on the next several slides. So we've probably all seen this VI characteristic of a MOS transistor before. And there's, aside from cutoffs, there's two main regions of operation. You have the linear region where it kind of looks like a resistor. And then you have the saturation region where it, it kind of looks like a flat device. And I hate to do this, but I'm going to throw up some equations up here. So you have an equation for the linear region, an equation for the saturation region, and then right where you switch from linear to saturation, that's called VDS sat. That's about the lowest voltage you can go to out where it's still in saturation. And here's what all those different terms in these equations mean. Now, again, I hate to throw equations up here, but last month, Michael threw an equation with an integral and a derivative up here. And I told him I was going to give him some crap about it. So I figured I could throw up a quadratic equation, no problem. Okay, so all right, so current mirrors, they want to operate up here in the saturation region. You want to stay away from linear. You want to stay up in saturation, and I'll show you why in just a minute here. So in saturation mode, a constant VGS, which is what you're going to get out of that mirror structure, produces a drain to source current that's almost constant for a wide range of drain to source voltages. You can vary the drain to source voltage all over the place, and you get the same drain to source current for as long as you keep VGS constant. This is the basic idea behind a MOS current mirror. So the combination of IREF and P1 creates a reference voltage here, and you apply that reference voltage to P2. So as long as you keep P2 in saturation, meaning you keep the voltage across it high enough so that it doesn't go down into the linear region, you're going to get an almost constant current through here. And if P1, the size of P1 matches the size of P2, and by size I mean the W over L ratio, width over length ratio, the current in this branch and the current in this branch are going to equal each other. Now, if you change that ratio, let's say you doubled the size of P2, well, I'll show you in a second, you can double the current. So you can use these width over length ratios to as a scale factor. So once again, this is the scale factor I mentioned earlier, and it's a result of this IDS saturation equation. And you can pretty much ignore the rest of this equation. Just look at the W over L here. What this is telling you is the drain to source current is proportional to the width over length, the size of the device, times a whole bunch of other stuff, but it's proportional to the width over length. So by ratioing the width over length of these devices, you can get double the current out here, or half the current out here, or 10 times the current out here. And it's just based on the ratio of the width over length of these devices. Now, you can stack a whole bunch of output current devices on a single reference current. So here we have our reference current, and it's going into this diode connected device just like before, and we're creating this VREF voltage. But now we're applying this VREF voltage to a whole bunch of output transistors here. And these transistors don't all have to be the same size. They could all be different sizes. That means IL1, IL2, 3, 4, they could all be different currents. But they're all going to be somewhat proportional to this input current. Now they could be larger, maybe double, or they could be smaller, maybe half. But it's based on the ratio of the width over length of these devices to the width over length of this device here. So you can see this ratio comes in really handy when you need to generate a lot of on-chip currents. So you can add NMOS devices when you want to mirror currents off the negative rail. So here I start off with an IREF current, and it's generating a current, and I have my width over length ratio set at 1 to 2. So that means this current is going to get gained up by a factor of 2 and appear over here. Here's our diode connected NMOS device. And here I flipped the switch here, or flipped the script. I went 2 to 1. So now I'm reducing the current. So I gained the current up by a factor of 2 here, but now I'm reducing it by in half. So what you get out here is really the same current you started with. We jacked it up by a factor of 2, and then reduced it also by a factor of 2, and you end up with about the original current. I'm just doing that to illustrate that you can gain current up, you can gain current down, you can mirror it off the negative rail, you can mirror it off the positive rail. Okay, sometimes you want to be able to enable or disable all these current mirrors. And this is done by adding some logic and some pull up, like a P3, or a pull down transistor like N3. So this is the exact same current mirror we looked at before, but now we've added everything in red here that represents enabling or disabling this current mirror. So if this enable pin is pulled high, you can see that N4, this is a buffer, N4 is going to be on, and that lets this current flow like normal. P3 and N3 are going to be off, so they don't do anything, and this current mirror works like normal, just like we said before. However, let's say you want to go into power down mode. And a lot of times, we're producing parts that have to go in, battery powered, integrated circuits. So you want to be able to go into power down mode. If you pull the enable pin low, that shuts N4 off, that kills this current, then turns P3 and N3 on. P3 pulls the gates of P1 and P2 up to the positive rail, that shuts them off. N3 pulls the gates of N2 and N1 down to ground, that shuts them off. So it puts this whole thing in power down mode. So this allows you to draw almost no current through these things, and it's a nice feature to have. Sometimes resistors are added to current mirrors. Now I just show a couple of resistors added in here. And these are known as source degeneration resistors. You've probably heard that term before. Now, these resistors can be stuffed in here, and they can somewhat improve the matching of these current mirrors if the resistors match better than the transistors. But that's usually not the primary reason for adding these resistors. Typically, you're adding source degeneration, and I'm not going to go through the equations, but they increase the impedance looking into the drains of these current mirrors. And if you were designing, say, an amplifier and you needed a high impedance node to make a lot of gain in that amplifier, adding source degeneration could give you more, much higher impedance on your high impedance node and allow give you more amplifier gain. You'll see these source degeneration resistors a lot of times in schematics. Notice how they're ratioed. In this case, we said we were doubling the current. 1x in this branch, 2x in this branch. Well, look at the resistors. We're not doubling the resistors, we're cutting the resistors in half. So the resistors ratio exactly opposite to the transistor sizes. And that's because we want the drops across all these resistors to be the same. We want this voltage drop to be the same as that voltage drop. So if we double the current, we're going to cut the resistance in half. Now, again, if you're using the unit cell approach, if you want to cut the resistor in half, you just put two of the same resistor in parallel, unit cell. Okay, so if all transistors had this flat characteristic that I'm showing up in the left here, it would make using current mirrors very, very easy. But unfortunately, transistors have a noticeable slope in their saturation region. And that's caused by something called channel length modulation. And that's due to this extra little term here in the IDS equation. And I just want to discuss that just briefly here. So in MOS transistors, the 1 over lambda term is akin to the early voltage in a bipolar transistor. And I'm sure all the fab guys talk about early voltage all the time on bipolars. Now, this is in bipolars, it's due to base width modulation. In MOS devices, it's called channel length modulation. And this slope, due to the channel length modulation, can cause mismatches in these currents. Let's say you have this current mirror here, and the drain to source voltage on P1 is at this location. Ooh, and the drain to source voltage on this guy is over here. Well, now, because this is not a flat region anymore, it's a little bit of slope, now you get this mismatch. If this was nice and flat in here, oh, these currents would match very well, but now they don't match very well because of channel length modulation. And here I just want to show what channel length modulation looks like from the device standpoint. You can see as we increase the drain to source voltage here, we get a depletion region forming around the drain. And that depletion region starts eating into the channel that we're forming between the source and the drain here. And if we increase the voltage, you can see it eats into the channel a little bit more. Oh, let's increase the voltage a little bit more. Oh, that depletion region's getting bigger and bigger and bigger. And you can see at high VDS voltages, this depletion region has really cut into the channel. So what that does is it makes the channel look shorter. You don't have, so the W over L has the effect of being larger because you've cut the L part down. That's what gives you that slope on the IDS versus VDS curve. Now, what can you do about that? Well, let's say you use a long channel device. Here I've drawn a similar device, but now it's a very long channel. We're going to go through that same exercise where we increase the VDS voltage. And yeah, it starts eating into the channel as we add drain to source voltage. But you can see it's only affecting the channel by a small amount. Most of the channel stays where, the same length it was before. You're only varying a little bit. So what this says is that long channel devices are going to be much flatter in the saturation region than short channel devices. And I try to show this on this slide here. A long channel device is going to look pretty flat in saturation region. So for current mirrors, long channel devices are probably what you want to use, or at least this is one of the tools in your toolbox. Now, using long channel devices, you pay an area penalty. If they're longer, you usually have to go wider to make them work. Using a Cascode configuration, this is a circuit configuration, is another means for reducing the effect of channel length modulation. And what we've done here is we've stacked a couple of devices, and now you can see we have two diode connected devices here. So when we run Iref through here, we're going to create two reference voltages, V1 and V2. And if we figure out, you can see V1 is going to be 1 VGS down from VDD, V2 is going to be 2 VGSs down from VDD. But over here, we have another VGS, so V3 is going to go up 1 VGS. So you go down 2, up 1, that leaves 1 VGS for the drain to source voltage across P2. Well, the drain to source voltage on P1 is also 1 VDS. And it's kind of hard to explain, but let's look at it from a graphical standpoint. What this circuit does, it takes the two current mirror devices, and now it forces them to work at almost the same VDS voltage. So even though you might be on a slope, instead of having one down here and one down here, this Cascode configuration forces the two to be almost at the same voltage. That way you get almost the same match current that you would before. The only problem with this technique is it adds headroom. You need an extra VGS. So if you're going to try to use this in a low voltage application, yeah, you might run out of headroom and you might not be able to use this configuration. So there is another configuration here, and I'm almost done. I know I'm running out of time. This is called a low voltage cascode, and you bias this up so that let's go to the next slide. The idea here is you're going to try to pick the right bias voltage to minimize the drops across P1 and P2 so that they're just barely in saturation. And you do that by creating a source here that's VDS plus VGS. And it's kind of hard to see, but you come down by VDS plus VGS, go up 1 VGS, that leaves VDS sat across these devices, which is the minimum voltage you can go to and still keep these devices saturated. This type of circuit is often used in ICs that have a very low power supply voltage requirement. The problem is it costs a bunch of extra circuitry. And here I just show how you might generate it. And I'm sorry, I know this is diagram is getting a little confusing here, but this is how you would generate this VDS plus VGS, or one possible way of doing it. I'm not going to talk about this in great detail, but you can kind of see we create a copy of the reference current and then run it through a couple devices and use that voltage to bias the gates of the Cascode devices. Once again, this is you can use this as a low voltage Cascode current mirror. It just costs you a bunch of extra devices to build. Okay, so this is the quiz I talked about. I threw this circuit up here, and you look at it and say, oh boy, there's a whole bunch of transistors up here. How do I know what any of this stuff does? And so let's go through. So if you look at this, you can see some of these are pretty obvious. You've got current mirrors. You can see the diode connected devices we talked about, the rails where we're generating current. Here's our diode connected device. It's generating reference voltages. And the next part is, oh boy, look at all these transistors here. This is part of that enable-disable circuit that we talked about, where we want to be able to power down the op amp and turn it, kill all the currents so that if we're running off a battery, it doesn't drain the battery very much. And that's what everything in green here is. And then the last thing I wanted to point out was all this circuitry in the middle here. This is part of that cascode or low voltage cascode circuitry. We have a bunch of cascode transistors here, and all these transistors here and here are the bias to bias up the cascodes. So if you notice, there's not many transistors left. You maybe have the input pair, the output pair. Everything else is kind of related to current mirrors. So just wanted to give you an idea what that kind of looks like once you get used to seeing these things. So analog IC schematics and layouts can be very confusing to follow. However, most analog ICs are designed using a common set of techniques and practices. So once you begin to understand these practices, analog circuits start to become easier to follow. Today I talked about matching, unit cells, and current mirrors. All of these techniques are very commonly used. And I hope my talk gave you some new insights into the world of analog IC design. I do want to mention there's a glossary of terms at the end of the presentation. Look through this if you have a chance. Thank you very much for your time.